So welcome everyone along. We've got Professor Chris Faber here from the University of Southampton, University of Birmingham. Slip of the tongue, I forgot what I was talking about. So yeah, from the University of Birmingham, where he's the chair of pervasive and ubiquitous computing in the School of Computer Science. He's got a range of research and teaching experience in human interaction with technology, including how humans form teams with intelligent technology and sensor-based human technology interactions. And he's also leading an EPSRC project titled Human Robot Satisfying Trust, due to start early next year. So yeah, Chris, if you'd like to take it away.
Thank you. So although I'm doing the talk, the project involves people from Bristol, Loughborough and UCL. I've got their names up on here. And although they've seen some of the slides, none of what I'm going to say is their responsibility. So there's a disclaimer for that. If you go on to the next slide, please, Casey. Okay, so this is the project. It's a very messy slide, but the boxes in blue give you a rough idea of what we're trying to do. So we were awarded the project from a Trustworthy Autonomous Systems for Military and Security sandpit in Manchester in November last year. Was it November last year? It's been a while. And we formed a team, wrote a proposal, got into the final three, got funded and so on. So what we're interested in is understanding how people might work with semi-autonomous systems such as robots, and how they might manage trust. And a bunch of things on the left-hand side. We've got an idea of a ladder of trust, that trust goes up and down. We've got an idea that there are behavioral signatures of trust, that you don't necessarily have to keep communicating with your teammates in order to be able to trust them. We've got an idea of distributed situation awareness. That is, that there isn't a single homogeneous picture of the situation that you're responding to. Everybody has a different perspective and a different view. And part of teamwork is to work out how best to align those different views in order to achieve an overall goal. And we want to look at counterfactual reasoning. So if there are alternative ways of thinking about the situation, how might we manage that? And across all of these different activities, we're working with notions of trust and accountability from a legal perspective and an ethical perspective. So that's feeding into some of these other activities. And thinking about how we might combine modeling of human robot systems through reinforcement learning in particular, with experiments with real people and real robots. So if we move on to the next slide. Thanks. One of the comments that we had on our proposal was that we were saying that robots should trust humans, and a reviewer said, "Why are you doing that? How can you possibly say that robots can have something like trust? Surely that's just a human thing." And so the point that I'm making on this slide is that human perspective of trust sees trust as being a disposition, that you have a propensity or personality that allows you to trust technology or not. And of course, if we start thinking in terms of robots from that perspective, then we have to give robots a theory of mind, which I don't like and I don't really agree with. And so what else can we do? How can we think about trust from the position of a robot without assuming the robot's got a theory of mind? So we think, first of all, we can begin by saying that perhaps a robot can perceive the reliability of its teammates in terms of what actions they perform, whether they're achieving a goal that the robot has been programmed to pursue. And we can also perceive the commitment of those other teammates towards a shared outcome. So in other words, there might be individual level goals that are being pursued by the robots and teammates, and there might be a team level goal, which at some point might conflict with the individual. So let's move on to the next slide. Thank you. So one way of thinking about this is from a paper that's just coming out. In fact, this came out after we wrote our proposal, but it's from John Lee. And if anybody knows human factors work in the field of autonomous systems, then they would have come across John Lee's name, and he's done a lot of work on trust. His paper by John Lee and C, back in the early 2000s, I think, is one of those sort of seminal papers that think about how do you measure and evaluate trust. So the work that he's been doing more recently has moved from trust as being something about the person's about a disposition, and more to the transactional relationship. He calls that the sequence relating to a situation. So the idea is that individuals within a situation can pick up signs and signals from each other. This is what he's calling the semiotics, that are then interpreted relative to a view of trust, which he's thinking of in terms of responsivity. So within a cybernetic system, responsivity is the gain that's used to adjust between input and output. And if there are changes to input, then what you might need to do is to modify your output, your behavior relative to that input. From that perspective, the situation is the environment in which you're operating in, and your teammates and their behaviors. And the strategy is the best way of pursuing your own activity within the environment relative, or the situation relative to what your teammates are doing and the goals that are being achieved. And this then combines into a sequence of actions that are being performed. And we see that sequence of actions in terms of our ladder of trust, that you're moving up and down in terms of how confident you are that you can trust your teammates. And we assume that sometimes it's perfectly okay for you to perform an action when you don't trust your teammates, or perform an action when your teammates won't trust you, relative to whatever goals you're trying to pursue. So let's move on to the next slide. And there are analogies, and a whole bunch of analogies with how animals and non-human species might manage their combined behaviors. And within the world of biology, this is called social learning, that what you're attempting to do is work out the ways in which you might cooperate with other members of your species in order to pursue your species level goals or individual level goals. Often in social learning, this comes down to getting something to eat, I suppose, or someone to mate with. So there are a whole bunch of strategies which are about whether you copy what your peers are doing, or which of the peers you copy. And we see this as being something which is observational and transactional rather than dispositional, more so transactional than it is dispositional. Obviously, you need the disposition to know what defines the majority and what defines when you start copying. But we think it's important here that these particular species aren't necessarily forming or relying on a theory of mind in order to explain what their peer is doing. They are behaving because that is what behavior looks like in that situation. Let's move a little bit forward. Next slide. So if we assume that trust is dispositional, then it is going to relate to or be proportional to the actions that teammates are pursuing in terms of their own individual goals, and that they're pursuing in terms of team level goals. And that the strength of those different goals might vary depending on opportunity within the environment. If it's possible for you to pursue an individual goal at a low cost to yourself, you might do that. If to pursue a team goal, there's a high cost to yourself, then there's a trade-off between whether you think that team goal is really beneficial or whether you want to take the risk. So we think that the model of teammates should include the predictability of your teammates' actions relative to the current situation. And one way of thinking about that is that teammate doing something that I would do? in that situation, or are they doing something unexpected or different? Then some notion of capability. So is that teammate actually capable of performing an action in that situation? And then integrity. Does that teammate look as if it's pursuing its own goals, or whether it's pursuing goals relevant to the team? Now, this notion of predictability and capability and integrity implies a theory of mind, in that you're building a mental model, perhaps, of your teammates. And what we want to do is to say, can we have some measures of these three things that don't involve a theory of mind? And you can see from the reference at the bottom of the paper, at the bottom of the slide, that the fundamental proposal that we're looking at is one which is relying on entities that don't have a theory of mind. So we could perhaps pre-program behaviors or expectations of behavior relative to situations. We could pre-program capability in terms of a definition of what teammates are able to do. And then integrity might be the history of interactions that you've had, based on, is that teammate more likely to pursue their own goals or more likely to pursue team goals? Let's move on to the next slide. So one way of thinking about this as a non-communicating activity is by thinking about Barami's idea of optimally interacting minds. What he did was to give people, groups of people or pairs of people, I think in the first experiment, perceptual grading tasks. So that's in A. You can see there are very faint grey lines there. And the experiment was to say which of those lines was different. And it's really hard to do. And you adjust the perceptual grading so to make it really, really hard to do. And then you've got two people giving an answer. And what tends to happen is that the person who is the most confident is the one that sets the threshold for the answer. If both people agree, then it's definitely that one. If one isn't sure, then that person will go with the more confident person. And in some previous work, I working with a PhD student, was able to show that if you have the situation where humans interact with technology, then when people aren't quite sure, they will take the technology's response. So it seems to be that people will work on the basis of their own level of confidence relative to a decision. And if they're not sure, then they're more likely to adopt what the technology is saying, unless they believe that the technology is really bad, in which case they will go with their own judgment. So they're making this sort of confidence trade-off. But the point is that with very limited communication, and potentially just observing the outcome of a decision, people can balance their behaviors in such a way that they can reach a Bayes optimal level of decision making. So let's move on to the next slide. So supposing we then think about this not just in terms of about decision making, but in terms of the transaction between you and another person or another agent. So there are two agents on the left-hand side, two agents who are going to going into a room where there may be a threat. And we've just color-coded the threat as a red person. So depending on the capability of the agents, they would decide which one is going to go first. So if they trust each other, if one of those agents trusts themselves to be able to cope with this situation, they may put themselves forward and say, I'm going to go in. And if the other agent trusts that first agent, then they will let that happen. So there's a relationship perhaps in terms of level of trust based on capability and predictability and integrity. If the second agent believes that the first agent will act in such a way to protect themselves and the second agent, then they might trust that agent to go first. And the circle that we've got here is based on some work done by Kevin McKee and his colleagues. He was looking more in terms of social learning with animals, in terms of how they may modify their behaviors, but we're adapting this to think about humans and robots as how they may adapt their behaviors relative to their trust in the other agent in the team and themselves. So there's that trade-off. So if we go on to the next slide, not surprisingly, a model that we're starting to work with is prisoner's dilemma. And I say not surprisingly because the prisoner's dilemma is all about whether it's rational to behave in such a way that protect your own interests, or to behave in such a way that you can, if you like, share the risk between you and another person. So if you remember, in prisoner's dilemma, two prisoners have been interviewed for a particular crime separately, and their choice is whether to confess to the crime, and there may be a risk in doing that, or to keep quiet, or to say the other agent did it. So the choice is to keep quiet, to confess, or to grasp on the other person and say it was them that did it. And there's a payoff matrix that prisoner's dilemma has that depending on which choice you make, you either get away and have serve no time in prison, or you serve 5 years or perhaps 3 years. So if we then translate that a little bit and say that the relationship is between whether you pay attention to what your teammate is asking you to do or you ignore them, we can define payoff matrices that reflect a similar sort of structure to prisoner's dilemma. And one of the interesting things about prisoner's dilemma is that if there's no fixed limit to the turns that are being taken, if the sequence is unbounded, then you're more likely to cooperate, to pick an option which is protecting both you and your teammate. If there is a limit, then you're more likely to pick an option which protects you. So in prisoner's dilemma term, if there's a limit, then you're more likely to pick the option that is grasping on your teammate or the other person and not confessing. But if it's cooperative, then you're more likely to either keep quiet or confess. And modeling suggests that typically you base your decision on the single previous interaction. So in other words, that the decisions are n-1 rather than across the whole sequence, which means that you don't really need a theory of mind. You just need a history which is based on what's just happened. Although there was an interesting study from Southampton a few years ago where it was suggesting that you could get your teammate to identify themselves through a sequence of behaviors. So you'd have a sequence of, I think, 7 behaviors, and then once you'd seen that 7, then you would recognize them as somebody that was on your team, and then you would work with them. But we haven't seen human-robot interaction from a robot perspective using prisoner's dilemma. There was a paper from Edinburgh, I think last year, a couple of years ago, looking at what humans might do in a simulated environment, where they were looking at the number of choices that you had and the payoff. And the suggestion was that people had a tendency to look at the payoff if they only had a single interaction, but in a sequence of interactions, they would follow what the robot did in a tit-for-tat sequence, regardless of the payoff, which I thought was interesting. So let's move on to the next. And so as we play around with the payoffs, we can see that there are different sorts of relationship that are possible to model, that you can begin to say, what's the most likely set of behaviors that we can expect to see? And if we want our system to be mostly cooperative, then we can create something which is through a payoff matrix where we have a high likelihood of cooperation. If we change the payoff matrix, we can see that the individuals in model 3 require 2 sets of information before they make a decision So they'll base their decision on an accumulation of two sets of behaviors. So this is slightly less trusting of their teammates. If you move on again to the next slide. So again, going back to social learning and animal behavior, there's a notion called Hamilton's rule that your likelihood to trust or to cooperate is going to depend on your on the family relationship, the genetic relationship between you and other members of a group. So it's a reproductive or kin selection. Some interesting work has been looking at whether it's possible to simulate that, not through genetic relatedness, but through social construction. And there's a tendency, or there's a way in which that is being done through the image that is being presented or perceived by teammates of an individual. So an individual might be perceived as being more trustworthy than others, that its image then means that it's more likely to be cooperated with. Even if there isn't complete information. So as long as the population is able to share information about individuals, and there's some identity to those individuals in terms of their trustworthiness, then that can be used to affect the likelihood towards cooperation. And so we see that as relating to our concept of integrity within the model that we have. If we move on to the next slide. And some work that Mirko Mussolesi and colleagues have been doing prior to our proposal is to use reinforcement learning to build the propagation of image within a prisoner's dilemma environment. So as you start sharing information about other agents within a network, you modify their reputation, which is the image score, and that then enhances the likelihood or increases the likelihood towards cooperation relative to having no information. So the point of this is that through a relatively simple Q-learning reinforcement paradigm, it's possible to build models of how likely it is for trust to occur within a network or a cooperative environment where you've got a team of agents working together. So let's move on to the next slide. So in a thought experiment, where we're currently constructing this at the moment, we're going to have a maze which has got a series of gates plus tokens to recover. The idea is that when you go through a gate, you block off one of the other potential pathways, but you might also land on a red square that we've got on here. What that red square does is to disable the robot so it stops moving, but it reveals some hidden tokens. So for the human in the maze, it might be a good idea for the robot to keep stopping because then it shows where the tokens are. For the robot in the maze, it might be a bad idea because it doesn't want to stop. So we start to produce these different trade-offs in terms of where you might go, whether you might go through a gate, whether you might want to stop on these, or to have the robot stopping to activate the hidden tokens. We go on to the next slide. It makes it a little bit clearer. So we might then start to generate some individual goals for two humans and a robot within a three agent team. And they may have different behaviors or actions that they can perform. And so you may then have an expectation from the other teammates on the capability and predictability of whether an agent can perform an action. So the robot, for example, can open the gate and it can activate the hidden tokens. And so one of the human who is collecting the tokens might want to make sure that the robot keeps going on the red squares to reveal the hidden tokens so they can collect more. The human who is controlling the maze following might want the robot to avoid the red squares and go through particular routes, opening and closing gates to complete the maze as quickly as possible. So if we go on to the next slide, we can see an example of how this might work. That there's there's a robot in the team, there's human 1 and human 2, and there are actions that they can perform, a reward that they're trying to pursue, communications that they're going to give to their teammates. And what we're going to be modeling is whether it is rational for a particular agent to follow the communications, the advice given by their teammate, or to ignore it. And so that gives us a sense of how they might pursue their own goals or their team goals relative to the completing this maze. And what we're proposing is that in some situations, it's rational for a robot to trust their human team members in terms of what they're being told, or in terms of what they believe the human that's not quite right, in terms of what the human teammates are doing. And in other situations, it might be rational for them not to do that, to ignore their human teammates. And so as a simple example, if the robot has no information about its human teammates, the prisoner's dilemma models would suggest it is rational for it to pursue selfish interests entirely because it knows nothing else. Whereas if it starts to have some more information about its human teammates, prisoner's dilemma might suggest that under some circumstances, it's rational for it to cooperate and to look for that cooperation. And one of the questions that we're looking at in the first few months of the project is, can we start to define the limits of, if you like, rational behavior between ignoring and cooperating? If we move on to the next slide. So this involves us doing 4 things. So the first one is to think about allocation of function. Within the human factors literature, the allocation of function is deciding who does what. And there's a tradition of saying that under some circumstances, people do, if you like, particular types of decision making, and they're more creative, etc., etc. And robots or automation do things that require fast response and consistent response, and so on. And so there's a notion that humans are better at some things and machines are better at other things. But there's a limit to how true that is or how useful that is. And so more recent work has been looking at whether you can allocate functions dynamically on a sort of situation basis, so that sometimes you may have an agent in a particular situation who is not the best one for that task or function, but it might be better for them to do the activity in order for the team to move forward than it would be to wait for the more preferable agent to come along. So if we can define capability, predictability, and integrity of a teammate, then we can start making these situationally dependent decisions about who does what when. But this might affect trust, because it may be that what's being performed in a particular situation might affect the perception of trust or the rating of trust that other teammates have of an individual. So how do we manage to make that balance between who does what and how is trust maintained, and under what conditions might we sacrifice trust? So in other words, how might we move up and down that ladder of trust depending on the sequence and the situation? We think that's going to relate to the notions of goal constraints. So through the talk, I've been suggesting that there are individual goals and team goals in terms of the maze running task. But we also believe there may be some higher level goals that relate to the constraints on the behavior that's permissible in a particular environment or particular situation, particularly when we're thinking about military and security domains. So there may be actions that can be formed very, very quickly, but also very, very wrongly, or very unethically, or very illegally. So there will always be trade-offs between a particular set of goals at individual and team level, but also trade-offs in goals in terms of higher order constraints on the behavior. And bringing that into the mix of capability, predictability, and integrity, I think becomes interesting in terms of specifying the reward function or the reward space that we might have in reinforcement learning, but also in terms of the trade-off space between which goal should be prioritized at which point in an interaction? And if you're going to start changing that prioritization, how might you share that information within a team? And that requires distributed situation awareness, where it's not just about understanding your own local environment around you, but also the behavior of your teammates that you can see, and the behavior of the teammates that you might not be able to see based on an expectation of where they should be, what they should be doing, and how they should be doing it. And all of that compounded by the goals that might be being used to constrain behaviors. I think that was my last slide, because I wanted to, I wanted to give some time to see if anybody had, first of all, if anybody made sense of what I've just said, and secondly, if anybody has some questions that they want to, or comments or complaints. Happy to take all of those. I suppose I should apologize for presenting work with no data whatsoever. It's a bit uncomfortable, but the project hasn't started yet, so we don't have any data. So this is a perspective that we're taking and a position that we're taking towards the work, and thinking about trust, as I say, from a position of it being transactional rather than dispositional. Okay.
Great. Thank you very much, Chris.
Awesome.
Are there any questions anyone has to start us off? Radu?
All right, thank you, Chris. This is very, very thought-provoking. So I guess I have a question regarding the dynamic nature of trust. You explained that trust cannot be static. So does this mean that agent decisions will need to be made on the fly? And if that's the case, how do you verify that they are the right decisions in such safety critical, mission critical applications?
Yeah, I think that's really interesting, because if we're assuming that there are going to be, if you like, situationally dependent correct answers to doing something, then the verification becomes very, very tricky. At best, you can hope it's post hoc, but that's not much use. So I suppose what we're trying to do with our reinforcement learning modeling is to say that under what circumstances do these different variables, capability, predictability, and integrity, become critical in distinguishing between courses of action. And that then feeds into the counterfactual reasoning work package, where we say that perhaps under a particular circumstance, the most likely behavior is to open a gate, but that has a cost associated with it. An alternative behavior might be to route around, or to reroute, so you take a different path to get to an endpoint. And there may be a higher confidence in achieving the goal, but a lower risk. So you can begin to think about criticality of decisions as in terms of these counterfactual reasoning models. That doesn't necessarily answer your question, because it means that we end up with perhaps more than one way of doing something. But I think that's probably true of some of the environments in which we're going to be operating. And it starts to reveal, I guess, the cost and constraint on a particular choice of behavior, that under some circumstances you might choose an activity which has got a higher potential cost, where that cost may not be apparent immediately. It might be something which happens a little bit further along, in which case perhaps what the team needs to be doing is adapting itself to cope with the expectation or the predictability of another event happening. Does that make sense?
Yeah, no, absolutely. Yeah, in principle, with reinforcement learning, you would be synthesizing, right? It is policies that provide some sort of probabilistic guarantees, I suppose. So.
Right. And you would then run the model, or run a variety of models that would modify some of those constraints. So you would always end up with a suite of solutions rather than a single best solution.
Mm.
And that's where our counterfactual reasoning work starts, that we have that suite of models. And then what we're interested in is how would you then choose what would affect your choice of an action relative to the expected payoff or the expected reward?
Mhm. No, as I say, no, I wanted to maybe continue this discussion a little, and so something I noticed in the examples that you chose is that there is relatively little or maybe no communication between agents, like in the prisoner's dilemma, or even in this later example with the robot and the human. But in principle, in quite a number of scenarios, there is nothing to preclude communication and the agents sort of sharing their intention. I mean, when that's possible, a lot can be gained, presumably, from exchanging messages about each other's intention.
Yeah, I think that's a good point. And we're starting off with the minimal or highly restricted communication, mainly because that makes life difficult for us, but also because there may be in military and security situations a need to have limited communication. So if we can come up with a solution that works with no communication, then adding communication ought to make things better. Whereas if we start off with a situation where you require communication, then removing it will make things worse. But then the interesting question is, well, how much communication is needed and what needs to be communicated? So so for me, communication needn't be message exchange. It could simply be observing what your teammate is doing, because your teammate is within a visual range. So they by observing their behavior, they are in a sense communicating intent to you, even if that's not what there's nothing deliberate there. Communication becomes important when you don't see them, when they've gone around the corner and you want to then work out what they're going to do next. So you either want them to message you, or you may begin to build a model, a theory of mind of their behavior and their intention. And we also want that theory of mind to be as limited as possible, because we don't want to overcomplicate the robots in terms of what they're processing and how much they need to process prior to making a decision or a choice of action.
Yeah, very interesting. Thank you.
Are there any other questions? Yes. I had one question. It's just based on the ladder of trust and what that is as a concept. If you could, is it that situational, so that you go, or do you build up your trust up the ladder and go back down, or?
Yeah, so I think it's got two elements to it. One is the history of the interactions, or very recent history of interactions. And if you think about the prisoner's dilemma, then often it involves what's called a tit for tat, that you will do what the other player has just done. So you sort of repeat their behavior until you get to a point where you're more likely to cooperate. So you might adapt your behavior, or the robot and human team members might decide whether to pursue an individual goal or a team goal, relative to whether their teammates have pursued an individual goal or a team goal. So that's going to go up and down a little bit. But we also think that trust is going to be affected by the capability that's been given to one of your teammates. So, and we think that could be pre-programmed to start off with, that there just in terms of a function, that certain of the agents are able to do something and less able to do other things. So if in a situation you've got an agent that has pursued a selfish goal previously and has low capability, then your trust in that agent might be lower than if they had a higher capability and they pursued a team related goal previously. So you can start to see how this may go up and down. And we don't know the range in which it's going to go up and down, because we haven't decided what our scale of trust is yet. We're still trying to work out what we mean by trust.
Yeah.
We're dimensioning it against these three criteria.
Okay, thank you. There's a question from Callum.
Hi, can you hear me?
Yes.
Ah, perfect. So thank you. That was a really interesting talk. And yeah, so this might not be, I think maybe not the fairest of questions, unfortunately. So feel free just to tell me to go away. But I was thinking about, there was a piece of work that came out of Ishiguro's lab about in 2019. And what they had was they had a robot working in reception using a deep reinforcement learning network. And it was investigating the idea of limited experiences to be able to learn. But anyway, the idea was it would interact with the humans coming in and going. And it was trying to optimize the number of handshakes, the number of successful handshakes it was able to get. There was a couple other rewards, such as like being able to wave and all that. But reading the paper, I don't think I think it was kind of implied that what the robot was kind of doing was, it wasn't necessarily predicting what the human was going to do. It was, and you kind of hinted at this a little bit, which was the robot kind of manipulated the human user to doing something that it knows it can predict. So in the case of this robot in the reception area, it would wave, but it would initiate the wave to force the other person to wave back because it was able to predict that. Like it was this weird sort of loop with itself. So anyway, the reason I was thinking about this or bringing this up is, given that you're kind of looking at this sort of in a similar manner, but specifically in trust, are you not, or is there any concern, I suppose, of the robot like interjecting, like trying to manipulate the human user so that it can better predict what they're going to do, and not always for the positive effect? Because even as you said at the start, which is, if the human user is willing to put more trust in the robot, if it's not sure what it's going to do, are you not scared that the RL algorithm is going to potentially exploit that self-realized ignorance, perhaps?
No, I think that's perfectly possible, and depending on how we define the reward structure, that if we have a very high reward for team behavior, however that's defined, then the robot could quite easily, or the simulated robot in the reinforcement learning environment could conceivably only pursue team goals and not its own goals, in which case the team goals might actually suffer. So it could either end up aggressively pursuing something which isn't that useful, or it could end up pursuing something which has a much higher cost than it may be immediately apparent. And the way that we're thinking about that is that if you run a number of models with different reward structures, we should be able to create if you like, a space of solutions where we can identify costly choices and beneficial choices and less costly choices, where those choices may have a different history or different sort of play out from them. And perhaps, I don't know yet, but perhaps when we start thinking about that in terms of counterfactual reasoning, we can begin to identify at which point the team or agents within that team are showing a tendency towards one of those routes or another, which we may then want to have some intervention at. We might want to start saying, hang on, this looks like this agent is doing something which is less useful for the team. And we're thinking that not just in terms of the robot, but also in terms of the humans. It may be that the humans become stressed, the humans become confused, the humans start making mistakes. And so at another point where robots may not want to trust their human teammates, maybe where the humans are pursuing something which is locally beneficial, but perhaps globally inefficient. And what we're hoping is that with some of our reinforcement learning modeling, we can start to identify the points where that could be more obvious or more apparent, if that makes sense.
Am I allowed to have a follow-up question as well? Just because you touched upon it slightly. Yeah. So one of the other things that I've stumbled upon, oh God, this was years ago now, was this sort of interesting model regarding confidence within groups and group work and all that. And in the model they found that having one individual who's very overconfident so by their definition, it's somebody who's taken on more work than they're actually capable of. And you'd think that overconfidence in general would bring the group down. But in their model, what they found is that in theory, the people who are less confident or underconfident would feel more obliged to take on more work because they feel like they've not taken on enough. And then they actually are taking on the work that they are actually capable of doing. So overall, the group gets boosted. So it's that sort of psychological play that I'm sort of intrigued about, again, of introducing these sort of robots in these environments. Are you thinking that those who are already at a comfortable level of work might try to overexert themselves potentially to try to keep up with the robot, or to, like, you know, because I guess there is always that technophobia fear of, you know, robots are going to be here, or AI in general is going to replace us all. So I don't know. I mean, I'm not sure if this is something that this project in particular is going to be looking at, but I was just wondering if you had like any early thoughts on this.
It's not something we've discussed. It's really, but it's a really interesting point, and I should make a note of that and take it away, because how the team structures itself will be interesting over a period of an experiment. So we're beginning with relatively simple small teams of, you know, two humans and a robot, but we want to end up with three robots and perhaps 6 humans. And at that point, this idea of the allocation of work, I've used the phrase allocation of function, but you could call it work if you want to, or duties or tasks or whatever, becomes more important, and how that gets shared, and what even sharing might look like, whether that's just down to capability, or whether it's down to availability, or whether it's down to location. We don't know yet. But thank you. That was that.
No, great. Thank you for answering.
And then a question from Colin.
Hi, Chris. Thank you very much for this. So many interesting things. 2 things that occurred to me that maybe would be helpful if you could comment on. The first is, as a designer of these systems, it strikes me that with the robotics, we've got foundational capabilities, shall we say, of the robotics. We've got intentions of what we're doing and the outcomes, and we've got hazards. So any thoughts on how, as a designer, you should be viewing those things when thinking about trust? And then the second thing is, what is your thoughts about trust as a nonlinear metric? i.e. there's points in the threshold that are really important for trust. We'll turn it on and turn it off. But then actually there's a bit of a sliding scale between I don't trust it, but how much I don't trust it, and how we might reason about that non-linear space. Does that make sense?
Yeah. So so for the first question, I guess we're bundling that under the concepts of capability and predictability relative to the functions that are being performed. So there was a paper a while ago from Matthew Johnson using a method called Coactive Design, which I quite like. I mean, it's intensively manual, so it's not necessarily a very good engineering solution, but it maps the expected sequence of activities against the capabilities of agents, relative to whether they require some help or don't require help, whether they will perform that to 100% or lower than that. And then it gives a sort of a RAG rating traffic light to the different agents. So his Coactive Design paper was in a robotics journal. When was it? About 2013. And and he's Matthew Johnson from Florida. So that's quite a nice method. We've modified it a little bit by saying he didn't look at information requirements, and so we've then started to ask questions about how do you establish and maintain common ground, how do you deal with perhaps communications, going back to Radu's question. So that's one starting point, I guess, in terms of asking how do you produce, if you like, situationally aware modification and adaptability. And we're going to be using reinforcement learning models to play around with the settings of some of those parameters. It doesn't answer your question directly, but it's the route that we're using to explore how we might get a range of behaviors, and to start asking questions about where does performance start to break down, because I think that becomes interesting. Where breakdown may not necessarily be an error, it might be violating of a particular expectation or goal constraint. I think that then goes back to the second question, which is the non-linearity. I entirely agree with you that although we're talking about trust as a ladder where you go up and down, it doesn't necessarily mean that requires that to be a 3 steps up and 2 steps down. It might be jumping all over the place. And I believe that there will be situations in which trust is completely irrelevant, and trust is highly critical, and that what you don't want is to over engineer the irrelevant periods of time, and under engineer the critical periods. It's trying to work out when does trust kick in as that transaction in transactional terms. When does trust kick in to be critical? And when is it less important? And that's one of the reasons why we want to move away from trust as a disposition, because if you're worried about how humans perceive their technology as the basis of trust, then that might interfere with the transactions that are happening. That if you want to maintain a good level of trust all the time, then that requires 2 things. One is that there has to be some feedback to allow the person to maintain their trust. And secondly, there has to be some, if you like, theory of mind on the part of the autonomous system to decide what it should tell the person to be able for them to maintain their level of trust. Whereas if we see it as transactional and situational, that there will be periods of time where it doesn't really matter what everybody's doing, unless particular critical points are being failed or targets are being missed. Does that make sense?
Yeah. Yes, yeah, very much. I mean, I was interested in taking that further into the idea of strategies for building trust, but I'm rather worried that I get into RRI concerns there about, as Callum hinted at, the ethical nature of building machines that are able to work towards trust in a gaming sense. So yeah, it's fascinating stuff, Chris. Thank you.
Thank you. Yeah, and that gamification of trust, I think, is something that we're hoping to find in our reinforcement learning modeling. It will be interesting to produce models which are, if you like, over manipulative because of the reward structure that we've given them, and then to use that as a warning to say don't use that reward structure.
One would almost suggest that if you're using RL blindly, then gamification is almost guaranteed, right?
Yeah, if you just need 1 million runs, and then that's what you're going to get. but that points to the need to think about what a well-designed reward structure looks like, and how many components you might want to build into that, because you're optimizing against a number of parameters, which is what makes the concept of trust quite difficult, because there are a number of sort of hidden parameters that are probably influential, but we don't know how to define them. And then there are a number of more external parameters that we're trying to build into our transactional models.
Yes, thank you.
So the 2 ways of dealing with this: one is to have a really simple task to do, in which case you don't really learn anything. So even maze following might be too simple. So that's why we're trying to layer maze following into with more and more demands on individual agents, ending up with a point at which it might look a little bit stupid and unrealistic. And the challenge we've then got is how we then take that back to some of our sponsors in the military and say, this is like the work that you do, and they say, no, it isn't. We just do a patrol. So it's always that trade-off between what you abstract from a situation and what makes an interesting model.
Are there any other questions? No? Okay, well, we've finished slightly early, but yeah, it was really interesting. Some good discussion. So thank you very much, Chris, for your time.